functors, those are things we can map over. And we wanted like something like that, except that took a 2-argument function and let us kind of lift it up to work on, at whatever f's are. But functor is not enough to do that. So we talked about this new class, applicative. The word, I guess it comes from the term applicative functor. I think it's because, actually, the word comes from the fact that this operation, if you squint here and ignore the f, it just looks like function application, right? It's like a B to C function and a B, and you get a C, right? That's just normal function application. But this is like, well, it's function application, but in the context of an f, whatever f is. So we call f applicative because we can apply functions that are inside those. I think that's where the name comes from. So, right, and what this means, what it means to apply a function in the context of an f, it depends what f is, right? So we saw a few examples. So like, when f is maybe, this means, well, we're applying a function to an argument, but possibly something could fail along the way, right? And if either of those things is a nothing, then we'll just get nothing. Yeah. We saw like f could be, we could be reading this thing from some context. We saw, I believe those are only examples that we've seen so far. We'll see some more. So then, using that, we can indeed implement this fmap2. And then I think where we were last time is we said, if we want to do fmap3, would we need something completely different? Or will this work? And this works. So I think what I want to start with is, let's just see how the pattern continues. So I would like the three of you, you're going to have to move really far away. Just chat about this, see if you can figure out how you would implement fmap4. this point, the pattern's pretty clear. We can keep doing this all day because every time that we apply this app operator, it's like we get an F with a function that's kind of taking all the rest of the arguments, and we can keep doing that one argument at a time. Okay. Cool. Good. So let me show you a nicer way to write this. So first of all, the standard library actually defines this operator as a synonym for fmap. So this angle bracket $sign operator. So we can write this. So if I take this definition that we had, I can rewrite it instead of saying fmap gfa. If I use this operator for fmap, then I can write it in parentheses. I can put it infix like that. Yeah. And now, let's copy paste this one more time, because we can even write this a little more nicely, because these operators are defined in such a way that I think, this operator has higher precedence than this operator, and this operator is left associative. And that's, all that is on purpose, so that we actually don't need any parentheses in this expression at all. Why is it yelling? Oh, I know why. Because it's using the one that we made instead of like the standard one, and we didn't actually say what the precedence and associativity of this thing is, so it just got some default, which is not the right way. So actually, here we can see what the fix L for. Okay. So if I can just declare it. Okay, there we go. So I just gave it precedence level 4. The infix L means it's left associated. So, okay, so now it's not yelling at us anymore. So this looks nice, right? Because if you look at what we're doing, so G is just a function that takes a bunch of arguments, right? But these things, FA, FB, FC, FG, like, they're kind of almost the right type to be arguments to G, except they're wrapped in an F. And so this, like, if they weren't wrapped in an F, then we would just say G, A, B, C, D. We would just apply G to those things, right? But since they are wrapped in an F, we can't do that. But this still looks kind of clear. It's like, well, we're doing application. It's like G applied to a bunch of things. We just have to put these operators kind of in between arguments. And that means we're doing function application kind of in the context of this F, whatever F is. So in practice, right, you don't actually need to define, fmap 3, fmap 4, or whatever. If you want to do that, you can just use this notation in the first place. You can just, have your function, and we'll do a few examples. So we can just use this notation instead of defining, say, in the first place, instead of defining fmap 3, fmap 4, etc. Let's see a few examples. So like, so first of all, of course, I can just say like, so plus takes 2 arguments, right? And normally if I just say plus 2, 3, okay, say 5. But what if I don't have numbers, if I have maybe numbers? So if I have like, just 5, right? I can't apply plus to these directly because that wouldn't have the right type. But I can apply plus to them using the maybe applicative. I always put the angle $sign operator first, and then I just put the app operator in between all the rest of the arguments. So that applies the plus function in in the maybe context. So which means that, you know, if any one of them is nothing, the whole team is going to fail. But if they're all just, then it'll do whatever we get just. You know, we could do this with well, let's just define, you know, f of x, y, z is, you know, 3 times x plus 2 times y minus 2. And then I can say, so f is now taking 3 arguments, and I could say, you know, nothing plus 2 plus 5, and it's nothing. But if I put a just here, it's 6, but it does, you know, whatever the function f does on those 3 arguments. Right, and part of the thing that's nice about this, right, is that it lets you separate out, so the function f doesn't have to mention maybe at all, or whatever, right, it just does some computation, and then we can kind of deal with the fact that we actually have maybe in our arguments by using this notation to apply it. What if, okay, let's say this is actually so I have a function g, I have an fa, but I don't have an fb, I just have a b. I have an fc and I have a db. How would you implement this function? Any ideas? And let me remind you. Here's our class. So if I just use this implementation, it's going to yell at me because, like, you know, when I try to apply it to B, it's going to say, oh, I was expecting an FB, but this is not an FB, it's just a B. Yeah, Jack.
Would you use the same notation as above, but just instead of, or when FB and FD happen to be pure B and pure E?
Exactly, that's right. Yeah, because I have this pure thing, which we haven't used yet, but we're going to use it now. Right? Pure says, hey, you can always turn anything you want into an F, whatever. The reason it's called pure, one way to think about this is that F corresponds to some kind of so-called effects. So for example, in the case of maybe, it corresponds to the possibility of failing. That's kind of like an effect that can happen. And pure means we have a thing like that, but it doesn't have any effects. So in maybe case, it just always gives us just, like it doesn't fail. It doesn't really matter why it's called that. And it, you have to see a bunch more examples before maybe that starts to make sense. But absolutely, we can do this. So we can just say, I'll copy paste this to start, but then I can just say, oh, this is pure E. This is pure E. And again, right, I don't have to actually define. That would suck if I had to define, you know, a version of fmap 4 with every possible combination of f's and not f's, right? But I don't have to do that. We can always just write this, you know. So in our example over here, like, you know, let's say I was doing my function f, and I got, you know, 2 of the inputs I got from some place that could possibly fail, and I get a nothing. But, you know, the last number, you know, I get it, it's definitely going to be a number. So I can just say pure. It's the same as just, but in general, I can always do that. Okay. Let's see, what do I do now? I think I'm going to do a few more examples. Because at this point, we've only really seen maybe, and we've seen, I mean, maybe on its own is a very useful example, but let's see something. We've also seen this example that does, you know, reading from some E, but maybe that feels a little more abstract. So, let's do list. And so pure is going to have type A a list of A, and app is going to have type what? So it's this type, except f is going to be a list. So I have a list of B to C functions and a list of B's. I can get a list of C's. Let's just think about app for a minute. Like, what could app possibly do? There's actually several different reasonable answers that we could give. So what are some ideas again? How could, like, what could a function of this type could do? Okay, so you mean like take the first function and the first B, and then the second function and the second B. Yeah. So it can kind of do like a zip. Yeah. So one possibility is we could do a zip. I can apply first function to first argument, second to second, and second. Okay. Yeah, because right, each function we match with argument, I could apply that function and argument on the C. I can get my output. We would definitely have to, if these lists aren't the same length, we would have to just cut off the longer one, because once we get to a point where we only, I've run out of elements from one of the lists, then I can't really do anything else, because if I've got a B to C function, but I don't have a B to apply it to, I'm not going to be able to get a C. So that's how zip normally works. Okay, what else? You think of something else that this could do. Yeah, so kind of doing all possible combinations. Yeah. Yeah, we could. So we could, maybe one way to think of this is think of them kind of as like nested loops. So we're going to like first loop through all the functions. And for each function, we're going to loop through all the B's and apply it to all of them. Okay, we'll just like collect up all the results. So actually, let's say, for example, if I have like +1 times 10, 4, 5, we would get, in this first example, when we zip them, we would just get like 4, which is 3 plus 1, and then 40, which is 4 times 10. Right? But another is like combine in all possible ways. And using that same example, in that case we would get, we would first do +1, and we would apply it to all the inputs, right? So we would get like 4, 5, 6, and then we would do times 10 to all of them, and we'd get 30, 40, 50. So it turns out those both are sensible ways to define it. For various reasons that I don't want to go into at the moment, we can paste this in and see which one actually is the behavior chosen by the standard library. It is in fact that second behavior. So it applies, it combines them in all possible ways. There is also defined something called zip list, which acts like the other one. So that gives us 4. All right, but let's see if we can implement this second behavior. Leave this one down here. an A, I have to return a list of A's. Just a single one, yeah, that kind of seems sensible, right? You know, I mean, there's lots of choices. You could be like, oh, just return the empty list, right? But returning the empty list doesn't feel right because then we're just ignoring the A. You can repeat it a certain number of times, but that feels kind of like, you know, how many? It feels kind of arbitrary. It's like, oh, 6. Repeat it 6 times, like 6. So it turns out this is the correct definition, and we'll maybe think more about why that's the right one. But let's see if we can implement this. So what do you think I should pattern match on first? Yeah, I think that makes sense because since F is kind of like the outer loop, right? Like we first do +1 and we apply it to all those things. And then next we do times 10 and we do all those things. So actually, we're not even necessarily going to do pattern matching on B's at all because we just like we keep applying some function to everything. But this list, the first list, we want to go through it one by one. So I agree. So we'll just do this. So if I have an empty list of functions, what should I get? Yeah, we don't have much choice actually, because I have to get a list of C's as output. And if I don't even have a function for B to C, then I don't have any way to get C's. That also just kind of makes sense because if I'm kind of thinking of it as looping through this first list and then taking each function and applying it, it's like it'd be like a loop that doesn't even execute once, or I just get no result. So makes sense? Okay. What should I put here? Actually, why don't you all talk about it? So you can chat about it for a minute and figure out how we can implement this part. it on purpose? Okay, yeah, good. Maybe the worst is you're like trying to implement it and you load it up, but it turns out you're actually using the standard library version, you don't realize it, so it's just like, oh, mine works great. No, this looks like that works. You know, and we can like see what should happen here. It should just be empty list, right? That works. That works. It'll be like this. That was a silly way to do it, but yeah. So this, we can think one way to think of this as. You know, like we said, maybe, if you have a maybe wrapped around things, it corresponds to kind of introducing the possibility of things failing. Introducing this kind of list, wrapping this list around things, introduces the possibility of things having multiple results. And it's kind of like the universe branches at that point, and you like try everything, and you're like, well, what if this was the answer? Then what would I get? What if this was the answer? So like if I have, do I still have this function? This function f, right? Again, if I apply it normally, I just get a number. But if I say, oh, these are like, you know, there were 3 possible values for that first number, and you know, maybe there's only a single possible value for the second one, and the third one, you know, there's a couple possible values, and then, oops, no. Oh, right. I can't like just literally apply f. I have to use this notation. So I just get like, okay, all the possible results of running f if these are the possible values for these inputs. So that can be a useful thing, especially in those kind of scenarios where you're trying to like list all the possible something, right? You're like, well, do this in all possible ways and see what we get. Yeah.
So that runs 317 and then 617, or
say that again. It runs 317 and then 3119.
okay.
And then 617 and 6119. Yeah,
I got you.
Right. It's gonna go.
This takes all of the first.
Yeah, it really is like having nested loops, where like the outer loop is this thing. It's kind of going through that the slowest. And then, well, the fact that I put peer here, it's kind of like it's looping over it, but it's just like a single time. So, but if we not plus. Yeah, I know. So like first are all the things that end with 3. Right, and then yeah. So one thing I want to talk about, let's see if we'll just call this fmap. So I think I mentioned this the other day. I claimed that, let's bring up our definition of applicative again. I claimed that if we have some f and we have these 2 operations, this app and this pure, then we can actually implement fmap. So I want to see how to do that. Like, we're going to implement fmap using only these functions, okay? Which is kind of a proof that everything that is an instance of applicative really has to also be an instance of functor. Like, it automatically is, because another way to say it is applicative is kind of a stronger requirement than functor, because it's a subset of functor. Like, everything that is an applicative thing is also a functor. There are some functors that aren't applicative, but so chat about this and see if you guys can figure out how to do this. Kind of take this g as this function a to b, and we kind of wrap an f around it. So now it has type f a to b. And then now we can use f, because we have an f a to b and an f a. We can apply it. So this is actually a law required of every applicative. So it's not a law in the sense that, like, it's not an error. If you make a type and you make an instance of functor for it and you make an instance of applicative for it, and this is not true, that like so this has the right type, but the question is, if you do pure G app FA, will it do the same thing as what fmap does? Right? They could have the same type but do different things. And so Haskell will not complain if they don't do the same thing, but other Haskell programmers will complain. Okay? So it's kind of like you should always be able to transform, if you have pure G app something, you should always be able to turn that into fmap and have it not change the behavior. And then actually, if we go back, one interesting thing about this, if we think about, like we weren't quite sure maybe what to put for pure. We had this idea of what we wanted app to do. We weren't quite sure what to do for pure. This law actually determines exactly what pure has to do. So let's think about why. So for example, think about the applicative instance. So we must have, so fmap for list is just map, right? So map G of some A, the list of A's, should be equal to pure G at and if we think about, so map G A's, we know what that does, right? I have a list of A's, and we just apply G to everything in the list, and I get a list of the same length out with just G applied to each thing. So let's think about this side over here. So let's say that pure G, let's say that we defined it so that it just returns the empty list. It kind of obviously seems stupid, but we can see that it won't do the same thing anymore. Because if this is the empty list app, whatever is just the empty list. So this side would just be the empty list, and this side would be, some list of the same length of page. So that would work. Or if we made pure G, if we made it like, give us like 2 copies of it, right? Well now, if we had a list of 2 things here, and this list here, we would get 2 copies of everything in the output. We would like first map G over everything in A's, then we would do it again, because we had a second copy of G. We would map that, and we would get like 2 copies of it. So the only way to make this work is if pure G, in this case, actually just gives us that singles list. Because then applying that to something is the same as just mapping that one function. So which means pure G. I'll say which means there are some other laws, but that's the most interesting one in some sense. The other ones I don't really want to get into. Maybe about them if you like. All right. Any questions at this point? Yeah, actually, while we're talking about this, let's do this other possibility, right? So we said, well, here's another way that apps work on lists. So we're going to do the same thing as what the standard library does. We can't make 2 instances for the same type, right? We can't make 2 different instances for lists. So we can make a new type, just called zip list. All right, so this is really just, can you actually just use this syntax for me too? Sure, cool. So it's just a wrapper around a list of A's, right? Just so that I can give it a different instance. So we can make it a functor instance. That's boring though, so actually, we can do that. We might have to, I wasn't expecting that to work. I thought I was going to have to turn on an extension. But, cool. It turns out functor, I mean, once you've written a bunch of functor instances, you pretty quickly realize that like it's pretty mechanical, right? You just say, all right, let's pattern match on it. Just whatever constructor we have will return the same constructor, and then we'll just kind of recursively apply the function or map over all the sub things. And GHC can generate that code for us. And there's kind of only one way to do it. So there's not really any choice. So GHC can generate that code. So it's a functor, but we've got to make our own applicative instance. Applicative zip list. Where? So here is going to be from A to zip list A. And it's going to be from a zip list of functions to the zip list of arguments and give us back a zip list of results. And so we already know what this one we want to do. So we're just going to say zip list, and I'm going to say zip, I'm actually going to say zip width. So zip width, you give it a function, a 2-argument function, and it just goes through and applies that function, combines, the first, it zips together the two lists, but using the function to combine them. Instead of making a pair, it just applies the function and gets a result. So in fact, the function we want to use to combine them is, we could write it as the $sign operator just as function application. All right. So how about pure? I have to do a zip list. So the zip list, so we have to do a sum list of A's. And I claim that this will not work. Let's think about why, because we need to have this law here. So we need to say like fmap g, if I have a zip list of A's. And that's just going to be, we can imagine how this fmap's going to work. It's just going to give us a zip list, and we're just going to do map g A's. Right? But that has to be equal to pure g applied to zip list A's. Which is going to be, but right, whatever pure g gives us, it's going to take that list and it's going to zip it with A's. And it's going to take, each function here and apply it. It's going to take like the first function here and apply it to the first A, second function apply it to the second A, right? And we better get out, like this thing here is going to have the same length as whatever A's had. It's going to have all the elements that were in A's, it's just going to have G applied to every one of them. So the question is, how do I define pure so that those are the same? So that when I do pure G at this, which is going to zip this together with this, I get the same thing. I get a list of A's with G applied to everything.
Just the empty list?
The empty list?
Usually it will nothing when it would get the same number.
No, because when I do zip an empty list with something else, I just get the empty list. Because it just has to cut it off to whichever is shorter. Because if I don't have any functions at all, I can't, there's nothing to zip. Like I just have to, so that doesn't work. Okay, yeah, that's right. So I need this to have, I need as many G's as there are A's, right? If I have fewer things in here than there are A's, then it's going to get cut off, and I'm not going to get the same thing. So, but I just need to define pure by itself. I don't know how many, like this pure G doesn't get to look at A's, so it needs to return something that's going to work no matter what A's is. Exactly. We get infinite list of copies of G. And it doesn't matter, whatever we zip it with, there's going to be enough G's, right? The other one will always be shorter, so it'll chop it off to the length of this, and we'll just have as many G's as we need. And it'll, so yeah, that turns out this is the correct way to define this. So repeat just makes an infinite list for key. Yeah, it kind of has to do with, like if I'm going to do zip with plus, for example, I take two lists of numbers and I zip them together and I add corresponding numbers, but it always gets cut off to the length of the shorter one. What is the identity for that operation? It's not just a list with a single zero, because that would, whatever list I give it, it's going to get chopped off to length 1. Right? The only only possible identity is actually would be a list of, an infinite list of zeros, because then no matter what other listing you do, uh, this one is not as commonly useful as like, you know, the other listings, but I've used it occasionally. It's just an interesting example, and it's interesting to think about what the right way to do Q is. All right. Next time, I think we will we'll see how we can make a bunch of kind of utility functions that work with any applicative and give us some interesting, that do interesting things for, you know, for each different